Okay, I think we're live. So, how's it going, everybody? Coy, hopefully you're doing good. Oh, gotta mute this so I don't have to hear my stupid voice. I hate listening to recordings of myself. Does anybody else also hate that? Like, I feel like, man, if I really sound like that, people must like just hate being around me because that guy sounds like a total tool. Anyway, all right. So what we're going to start talking about today, how the warm-up exercises go and the video thing. That's Gucci. Yeah, good. Okay. Um, yeah. So integration by parts. What I think is a little bit ironic about this is, so let's think back to the derivative rules. You guys learn the basic one, you learn the power rule, and then we say, okay, what about products and quotients, and what about function composition? And you're like, okay, great. And then we do the product rule, we do the quotient rule, we do the chain rule. Well, which would you say is more challenging conceptually, the product rule or the chain rule? What do you guys think? Okay, chain rule, yeah. Um, okay, so then when we get to integration, other than just having the answer memorized, what's the only technique of integration that we know so far? Okay, use substitution, which is basically the chain rule, but in reverse for integration, right? And the chain rule is the more conceptually difficult one, but then that's the first one that we reverse. And it's not until Calc 2 that we say, oh, well, let's reverse the product rule, right? If we can reverse the chain rule, we can reverse the product rule. And integration by parts is, in a sense, the reverse product rule. So the idea here, right, is if I have the derivative or the differential um, of a product of two quantities, what does the product rule say? Well, if I've got two quantities u and v, then the differential of them is u times the differential of v plus v times the differential of u, right? So I'm writing this in differential notation rather than derivative notation because of what is about to happen. Okay, so good. That's just the product rule, right? No big deal there. Okay. You cannot see anything on the screen again, Cole? Okay. Oh, that's why, because I forgot to switch over to this. Sorry. There we go. Sorry, Cole. Yeah, I forgot to hit the button to take it away from my awesome splash screen. Okay, so right, so there's the product rule written in sort of differential style notation, and then just to be fun, let's integrate both sides. Right? Just slap an integral on both sides. Now, the right-hand side, what are those integrals? I don't know. That's the whole problem, right? But what about the left-hand side of this equation? What's the integral of d uv? uv, right? So an integral and a derivative sort of cancel each other out, and I am blowing off the plus c here, but you guys will forgive me. Yeah. Okay, so I've got that. And then what I'm going to do is solve this algebraically for one integral in terms of the other. And the way I choose to do it is to do it this way. It doesn't actually matter. Okay, and so I get this. And this is the integration by parts rule. Okay, so the idea is if we were confronted with an integral that looked difficult and was not something that a regular old U substitution could handle, then maybe what I could do is change this hard integral into a different, easier integral, right? So change the problem from something hard to something hopefully not as hard. And that's sort of the formula by which we will do it. Now, we'll have to be real careful and finesse this. But essentially, if you've got an integral, what you have to do is say, okay, I'm going to call this part of it u, and this other part of it dv. Well, you have to make that choice. And like with u substitutions, you have to choose wisely. Okay, so Ethan, I know I used this one last semester, but Indiana Jones and the Last Crusade, towards the end of the movie, what happens? They get to the temple that's got the chalice, and then the evil Nazi guy shows up and he picks one and takes the drink of the holy water out of it and then turns to dust because what happened? He chose poorly, right? So we have to choose wisely in this process. And towards later on in the class today, I'll give you guys sort of a trick that 99 times out of 100 will work. There are exceptions, but choosing u and dv, this is, I think, probably the reason why we wait on doing this in Calc 2, because with u substitutions, how many choices do you have to make? Just one. What's u, right? Here, we have to say, okay, I'm going to call part of it u and the other part dv. So in a sense, there's kind of two choices, right? And that maybe is a little bit more conceptually difficult. So anyway, all right, so let's look at an example of this where there's only one term, and so we're kind of forced as to what to do here. Okay, what's the trap answer on a question on this one? Right, okay, because that'd be the derivative is 1 over x, not the antiderivative. Okay, so in this case, what I want to do is I want to call part of the integral dv and the rest of it u. Okay, now, when I say dv and I mean a differential, okay, in this case, everything is a function of x, right? So dx, or d whatever, dt, dx is always going to be part of dv. There might be other stuff there too, but it'll always be part of dv, okay? Now, do we want to make dv equal to log x dx? I'll say no, because what do we need to know in the integration by parts formula? If we know dv, can we find v? How do we get from dv to v? Yes? Almost. Say which way? If we go from dv to v, antiderivative or integral, right? Okay, so if I made dv equal to log x dx, what would v be? The integral of that. Well, that's exactly the question that's in front of us. So that's not the choice to make, right? So the only choice that is sensible here is to let u equal natural log of x and dv equal dx. Okay, and I like to write things in sort of a grid, and I'm about to fill in two more things. So this is just sort of my, the way I like to notate it. Okay, so great. If u is natural log of x, what's du? 1 over x. No, because we're doing a derivative, not an integral. 1 over x dx, right, because it's a differential. Okay. All right, so we took the derivative, or really the differential of u, to get du. And then on the other side, we're going to take the antidifferential of dv to get v, right? So in this case, it's really easy. if dv is dx, what's v? X. Okay, now what really should it be? X plus c, because I just took an antiderivative. I will blow off the plus c until the very, very end of the problem. There's no need to introduce it right now. Okay, you could, but it's not necessary. Okay, so does that make sense? So we chose, sorry, we chose u and dv to be those two quantities. And then if u was log x, then du is 1 over x dx. If dv is dx, then v is x. Okay, and so now I know all four of the quantities that are in my integration by parts formula. Okay, so this here is u, and that's dv. And what does the integration by parts formula say this is? It's uv minus the integral of v du. Well, what is u and v and all of that other stuff? What's u? Natural log of x. What's v? X. What's v? What's du? Okay, and so we have that. Okay, so I just substituted in the four quantities, well, really three, I guess. U and v were log x and x, then minus the integral, and then the integral was v du, and we knew what v and du were, so we substituted those guys in. So what I've done is I've changed the original integral from the integral of log x to this new integral, which hopefully is easier to solve. This one it will be, because we've done it right, but that's the idea. Take a hard integral and turn it into a not quite as hard integral. Okay, good? Yeah? All right, so now what? Okay, right, so let's simplify this a little bit. The x and the 1 over x cancel. Okay, so that's nice. And then we have the world's easiest integral, right? What's the integral of 1? X. Okay, great. So we just get x natural log x minus x, and now I'll go ahead and throw in the plus c because we're at the end. Okay, so you still need the plus c, but we might as well just leave it for the very, very end, and it just simplifies. We've got enough mess to keep up with. Okay, so there we go. Now, how do we double check that this answer is correct? Okay, and if we were to do so, what rules would we need? Well, what's the derivative of x natural log of x? We need the product rule for that, right? That shouldn't be a shock that, because in a sense, we were doing the product rule backwards, right? So what we were doing is sort of recognizing that log x is a funny, in a disguised way, the result of having done a product rule on some problem. We just didn't know what that problem was until right now. Okay, does that make sense? Yeah? Now, in this case, our choice of u and dv were kind of forced, right? Because we only had one term in the integrand. What other options did we have? If we had tried to, well, two things. Your dx can never be part of u. Because what does it mean to take the differential of a differential? I don't know. Okay, so that's one thing. The other thing is that if we had put the log x with dv, then v would have been the integral of log x. Well, that's the exact question that we're asking in the first place, so that would be kind of circular reasoning, right? we can solve the integral for log x dx if and only if we can solve the integral for log x. Well, yeah, but that's sort of useless. Okay. All right. Good. All right. So let's look at one that's maybe a little less obvious. Am I good to go to a new page here? No? Okay. So the next one I want to do is, let's do a definite integral. Nobody said that these things had to be indefinite. Okay, in terms of the fact that this is a definite integral, we've got two options. We could just pretend it's an indefinite integral and deal with the numbers at the end. Okay, that would certainly work. But let's actually, for just a moment, go back to the integration by parts formula. Okay, this guy here. If these are definite integrals, then what's funny here is that the bounds of the integral actually don't change. Okay, because like in the example we worked, the new integral was dx, and the old integral was also dx, right? Well, since we haven't changed the variable of integration, the bounds will stay in the same terms, okay? So the version of this for definite integrals would be integral of from a to b of u dv is uv minus integral a, well, sorry, I messed it up. Okay, the integral on the right-hand side retains the bounds from the original one, but we have to plug in the a and the b to the uv term. Okay, so we can either do that as we go or do it all at the end. It's up to you, really. I'll go ahead and do it as we go, just for the sake of demonstration, although in practice, when it comes to definite integrals, I tend to blow off that they're definite, find the antiderivative, and then do the fundamental theorem, for the most part. Okay, so are we good with the sort of definite integral version? Just minor tweak. Okay, so in this case, we've got some choices to make, right? So we've got x e to the x dx. Some of that's going to be u, the rest of it's going to be dv. How should we choose this? Okay, so the first thing I said is what always will be part of dv? Dx, okay? So it's going to be something dx. I'll just leave some space there. So let's sort of think about this and use some strategery, to borrow a turn of phrase from President Bush. If I made dv x dx, what would v become? Mm-hmm. Is that more or less complicated than just x? Probably more complicated. Okay, so if we'd like to avoid making things worse than they already are, okay, so probably you do not want to put x as dv because its integral gets worse. Okay, however, is e to the x, what's its integral? Just itself, right? So that's no better and no worse. It's equally bad. And if I had let x be u, what's du? 1 dx. Well, that's simpler than just x, I would argue. Okay, so does it seem like what we probably should do is let u be x and dv be e to the x dx? Does that seem like a reasonable choice here? Yes? Okay. Once we've made that choice, what do you mean you cannot see them, Farden? You should be able to see a white screen where I'm writing. Sorry, Farden's on the chat and I guess can't see anything. You may need to refresh and restart playing the stream. And also, Farden, at the very beginning of the stream, I didn't have I forgot to switch the input, so you may just need to fast forward a little bit. Okay, so hopefully, yeah, so try that. Let's see. So if u is equal to x, then what's du? Dx. If dv is equal to e to the x dx, then v is equal to e to the x. Okay, so now we're going to do our rule, uv minus the integral of v du. All right, so let me fill everything in. So we'll have u and v, okay, from 0 to the natural log of 2, minus the integral from 0 to the natural log of 2 of v du. Okay, and let's make sure that I get everything in the correct spot. So I have uv minus v du with, of course, the integral in front of it. Okay, so I got everything in the right spot, hopefully. Okay, have we made our lives easier? Yes, because the new integral is easy. It's just e to the x, no big deal. Okay, and plugging in numbers to a term is also no big deal. So we'll have, let's see, x e to the x from 0 to natural log of 2 minus e to the x from 0 to the natural log of 2. Or I could combine these, of course, to be like that. And now let's start plugging in numbers. Okay, fundamental theorem. So what am I going to get when I plug in log 2? I will get log 2 times e to the log 2 minus e to the log 2. What do I get when I plug in 0? Well, I get 0 for the first term minus e to the 0 for the second term. And then because I'm an evil professor, I deliberately picked things with logarithms and e just to torture you guys. Can we simplify that? To quote a mother from Minnesota, you betcha, right? You betcha. Actually, just sort of reminded me. Have you guys seen Brave, the Pixar movie with the sort of magic and stuff? No? You have? Like, I think the mom is definitely like a Minnesota kind of mom. Yeah. So, okay. So, can we simplify this? How can we simplify this? Let me ask a. It's always bad to ask yes no questions. How could we simplify this? Yes? Okay, and it simplifies to what? Two. Okay, so we have log 2, can't do anything with that. That's 2, that's 2. And then minus, what's e to the 0? 1. I've got a double negative, so it'll be plus. And so I'll get 2 natural log of 2 and then I've got minus 2 plus 1 minus 1. I could also write this as, well, that. Yeah, the rainbow rule. I'm never going to forget that now, Will.
Thank goodness.
Yeah.
You were late for it.
Yeah. Okay, because of Will's rainbow rule. Right. So we could write it either way. Um, Probably the first one is the way I would stick just because um, I think for aesthetic reasons, it's kind of nice to have the simplest term inside the logarithm as you can, but that's sort of an aesthetic choice. Yes, okay, excellent, Farden. I'm glad that you can see now. And yep, Ben, that's what we got. And Ben, I got the note about Mathematica. I've got a couple ideas to work on that. I'm gonna look at it after class and come up with a solution. Um, okay, good. So let's try another one. You guys good? I'm gonna go to a new page and um, let you guys take a stab at this one. Okay. Um, so e to the x sine x. Choose your u and your v. See what you think would be a good choice, and then start to execute the integration by parts process. See what happens. So we'll just take a couple minutes, see what you think you might get here. Yeah, I really need to get Jeopardy music for the stream. What do you guys think? No, I could. I don't want to get sued though, or have Twitch banhammer me because of copyright. Well, or we could just use old Wabash, right? And those of you guys who are online, why don't you type in the chat what you'd like to make U and what you'd like to make DV, and let's see if you guys agree um, with choice here. We got 5 people in the chat. Yes, Coy, you see what I'm up to. Up to evil, pure evil. Okay, so Farden suggests, let's see what the room. Farden suggests making dv e to the x dx and u equal to sine x. What do you guys in the room think? Okay, so maybe the better question is why did you choose that, Farden? Um, yeah, Coy did the same thing. Let's see. Cole agrees. Looks like Ben, you agree also. Why is this a reasonable choice? Well, what do we have to do to get from dv to v? That's the hard part. We need to take an antiderivative. It's pretty easy to antidifferentiate e to the x, right? Now, similarly, we need to take the derivative of u And the derivative of sine is, that's not that bad, right? I mean, we just traded one trig function for another. Okay, fine. So yeah, so let's do that and see what we get. So we get cos x dx, and then we get e to the x there, and the integration by parts rule says, right, we'd have uv, so e to the x sine x minus the integral of v du. Okay, great. Right, so we just changed the integral from one thing to another. What's the problem? Is the new integral easier than the original? No, but it's not harder either, right? In a sense, because sine, cosine, right? Yeah, true, but we don't have to integrate that thing in front. It's just a term, right? So this integral, the resulting integral, is no harder, but also no easier than the one that we started with. All right. Well, what's the old phrase? If at first you don't succeed, try again. Okay, so we could start over, but let's just pretend that we didn't do that. Let's say, oh, well, okay, I've got the integral of e to the x cos x. If that were the original question, could I just do this process again? Now, maybe that's a horrible idea, but let's just do it and see what happens. Okay, so I'm going to let, now I can't use u and v anymore because I've already used them. Okay, so what I'm going to do is I'm going to put little hats on top of them, right? So I'm going to have u hat and dv hat. You could use other letters if you wanted, but I want to put hats on letters today. So we're going to put hats on letters. Is that okay? Yeah. Okay. So like before, let's actually make the same choice that we made before, which is to put the e to the x in the differential part and the trig function in the non-differential part. Okay, now this time we have the mild annoyance of there being a minus sign, right? Okay, but that's okay, we can live with it. Now here's where you got to be real careful. I'm about to change this integral into a bunch of stuff with the integration by parts rule, right? Put a bracket around it because otherwise you'll miss what's about to happen. So I'll have u hat v hat minus the integral of v hat du hat. Okay, like so. Good? Okay, let me simplify this a little bit. Okay, so we have e to the x sine x minus e to the x cos x minus the integral of e to the x sine x. And what was the question we were trying to answer in the beginning? Well, we were trying to answer this question. Oops, and I need a dx there. Right, so that's what our labors have gotten us, is that the integral of e to the x sine x is equal to that stuff minus the integral of e to the x sine x. Okay, now those of you guys who are online, you figured out the trick. Will, what do you think we should do? Add the integral of e to the x sine x dx both sides. Yeah, let's think of the integral of e to the x sine x dx as just being a gigantic variable. Well, if I've got a thing equal to some stuff minus the thing, then I can add the thing to both sides, and I've got two integrals of e to the x sine x equals this other stuff. Oops. Okay, so you guys see the trick, right? We're treating the integral as it's now an unknown quantity, and we're done with the calculus. We're just manipulating this algebraically. And this is, by the way, why you have to be really careful with the positive and negative, because if we had messed this up, then we would have gotten garbage. Okay, so just be careful with the signs when you do this. So yeah, all we've got to do then is just take the right-hand side, divide it by 2, and then now that we're finished, now that we're finished, of course, we have our plus c. Well, that was fun. Okay. So, yes, the evil part about integration by parts is sometimes you have to do it twice, or 3 times, or 4 times, or whatever. It can get kind of messy, particularly if you do it 3 or 4 times, because you're going to have minuses popping up all over the place, and it can be real easy to mix them up. But yeah, this is sort of a trick. Now, the other trick here, and what maybe made this work so nicely, is that notice that when we made the second integration by parts choice, we kind of kept the same substitutions as the first time. Namely, the trig function we made as part of u, okay, yeah, it's cosine this time instead of sine, and the dv part we made still the exponential, okay? Had we not done that, had we picked the opposite direction, then we would have just sort of gone around in circles and it wouldn't have really worked, okay? So, yeah. Okay, so yes, you might have to do this more than one time. All right, so let me go to, I'm actually going to share my screen because this will make it a little easier. Oops. I'm going to share my screen. So let's see, we want full screen. Okay, so you guys at home should be able to see my computer there and part of my ugly mug. Okay, so a rule of thumb that works 99 times out of 100 for how to choose u is this rule. Oh, I'm sorry, you guys on the screen can't see this. Well, blast. Let me just write it out on the iPad so that everybody can see it. Sorry, guys. Okay, so liate. Your hit list for you is going to be, your priority list is given by this mnemonic, and you're going to work your way from the top to the bottom. And what this stands for is logarithms, inverse trig, so that's going to be like arctangent, arcsine, those guys. Algebra, okay, so that's going to be stuff like x squared, square roots, etc. Trig, and exponentials. Okay, so stuff like that. Okay, so this is your sort of priority list for what you should choose to be u. And then what you don't choose to be u, everything else, is dv. So let's sort of think about why this is a good order to choose things in. And you basically start at the top, and if, like, for example, the problem we just worked, are there any logarithms? No, so just move on to the next thing. But why is this sort of a good idea? Well, this is the choice of u So why is it good that perhaps exponentials are saved for the very end? And that in most cases, you're not going to use those uh, as your choice for u. Yes? They don't simplify, but they're also easy to integrate. Okay, so if we don't pick them for du, that means we're picking them for dv, which means we have to integrate them. Well, exponentials are pretty easy to integrate. Trig functions. Are trig functions easy to integrate? Most of them, right? Sine and cosine are. If you start to have like secants and tangents, that could get a little messy, but it's not usually going to be a train wreck. Algebraic terms, why would it be better to differentiate them than to integrate them? Generally speaking, particularly polynomials. Yeah. Yeah. So if you integrate them, the powers go up. If you differentiate them, the powers go down. And down means smaller, and often that's better. Okay, from a simplification standpoint. Okay, inverse trig uh, and logarithm. Well, for that, let's think about when you take the derivative of a logarithm, do you have a logarithm in the answer? No, it turns it into 1 over x type things. Okay, well, that's a lot simpler than a logarithm. Similarly, what's the derivative of all of the inverse trig functions? Well, like what's the derivative of arctangent? Yeah, they're all rational functions, or they might have a square root in them. So like arcsine's derivative is 1 over the square root of 1 minus x squared, right? So there's a square root there. That means it's not technically rational, but it's sort of almost rational, okay? In particular, though, there's no trig function left, okay? So we choose the logarithm and the inverse trig functions to be sort of higher on our priority list for u in order to uh, sort of try to allow to simplify things as much as possible and save the easy stuff for the hard step, which is the dv to v step. Okay, so this this rule of thumb is, like I said, a rule of thumb. It's not 100% effective. There are examples where you this doesn't help you. Uh, we'll look at we'll actually look at one next time where deliberately doing something else is actually a better approach. Um, and but it's an easy mnemonic to remember. Liate. It's kind of like, you know we're almost to pumpkin spice latte season, so we just need your pumpkin spice liate. Yeah. Um, so anyway, interestingly enough, the book does mention liate, but I didn't see the reference to it. So um, I learned this rule probably in high school. Um, and it was definitely something that was in my bag of tricks for teaching when I got to graduate school and started TAing. Um, so my first job would help if I could speak English today. My first job out of graduate school, I was a visiting professor at Bradley University, which those of you guys from the Midwest maybe have heard of it. It's in Peoria, Illinois. And basically, I was replacing somebody that was on sabbatical for the year. Great. Well, one of the guys who teaches there, although he just retired, his name is Herb Kasubi. And like me, he's actually really interested in the history of math. So I had gotten to know Herb from conferences. Well, it was maybe 5 years ago, so I'm well into my career here at Wabash, when I actually found out he was the one who came up with Leate in the first place. Okay, so in 1983, I think it was, he published a short article in the American Mathematically Monthly, which is a sort of a periodical that it's one of several published by the Math Association of America. And part of it was it has a section on like teaching tricks and things related to teaching mathematics. And so it's like a two-page paper, but it introduces Liate and then gives a few examples of, that are sort of staple Calc 2 kind of problems as to this. So yeah, it's kind of cool to be just my office was just down the hall from the guy who came up with this. And yeah, it's sort of funny because I think probably every Calc 2 teacher now on the planet uses this because it is really handy, and I think students find it helpful to make integration by parts not quite as tricky because there is more to keep up with than with a U substitution. Okay, so the crap, it's 9:55. Okay, no, the document is not on Canvas yet, Farden, but I will put it up there. The other problem that I wanted to look at, and maybe why don't we do this? Why don't you guys try this and just see what you can come up with um, for for Friday? Okay, so this is sine of the natural log of x. It's not sine x times log x. I'm composed the two functions. Okay, I'm going to call this a spicy example. This one is maybe getting to like Asian zing level spice um, from. Have you ever been to Buffalo Wild Wings, the restaurant? Okay, well, so it's a chicken wing place, and they have sauces that go from really, really mild to like make you cry for a month. It's so spicy. Well, one of them that's sort of in the middle is called Asian Zing, and it's sort of it's got sort of Asian spice to it, but that's what they call it. So it's one of my personal favorites. So, all right, well, I will see you guys on Friday or in person, and I'll put this document up on Canvas so you guys can reference it, and we will see you guys then.